Okay, so let us start the exercises at the end of this section. The first few are going to be quite easy. In fact, we have the solutions available to us in the videos on knife set theory, but it doesn't hurt to do them once more, just once more. So this one has subdivisions or parts. Part A says if A is a subset of B and B is a subset of C, then prove that A is a subset of C. So this is the first part. Part B says if B is a subset of A prove that A union B equals A and conversely. That is, if this is the case, then we also have this. And part C, again, if B is a subset of A, oh, it is something else, okay. Prove that for any set C, both B union C is a subset of A union C and B intersection C is a subset of A intersection C. So the solution is very easy. The first one is almost obvious. Anyway, let's just, for the sake of completeness, let's go through them. So it is given that A is a subset of B and B is a subset of C. So we can write that down, given and we are considering any element x in A. Then x belongs to B since B is a A is a subset of B. So every element of A will also be in B, so x is in B, which implies x belongs to C since B is a subset of C. So this element x in B will also be in C. So any element in A is ultimately in C. Thus A is a subset of C. So that completes part A. Then part B. So here we have to prove that if B is contained in A, then this is true, and conversely, if this is true, then B is contained in A. So we have to prove both the things. So first, assume B is contained in A. we already know something, that A union B has A as a subset, that A is a subset of A union B. To prove equality, we have to prove that A union B is also a subset of A. So let X belong to A union B, or if you are not, we can take X. You see, here we have taken X, there also we are taking X. That actually does not create any confusion. It's because this should be viewed as a variable element, any element of A. Okay, so it's not that it is something fixed in A that we are considering. X just represents any typical element in here, say A union B. So we are using X here, here also we are using X, that is not a problem. Then according to the definition of union, X belongs to A or X belongs to B, or X belongs to both, because this or is inclusive or. If X belongs to A, then we are done. We are done means we are supposed to show that this is a subset of A. So if our element is already in A, then we are done. If however X belongs to B, then also X belongs to A. Why? Because B is a subset of A. So in any case, or instead of writing it like this, we can let me just phrase it somewhat differently. It is not looking really good. I mean, it's not looking nice. Either X belongs to A, or okay, we could have written this here itself, no? This implies either X belongs to A or X belongs to B, or both. Let us also write this in brackets. If X belongs to B, then X belongs to A, since B is a subset of A. So in any case, we have X belongs to A, and this implies that see, X was any element in A union B, now that is in A. So this implies A union B is a subset of A. Combine this containment with this containment to have equality. Thus A union B equals A. Now we have to prove the converse. Conversely, assume that A union B equals A. We now have to prove that B is a subset of A. Okay. So there is only one way to prove that. You take any element in B and prove that that element is in A. So let X belong to B. Since B is a subset of A union B. This is what we already know. In fact, we have used it here also. See, we already know that A union B contains A as a subset. Just like that, it contains B as a subset. Since this is true, we have X belongs to A union B. But now A union B is equal to A. So any element in B is in A. Thus, B is a subset of A. So the other implication, the converse, has also been proved. So this is part B. Finally, we come to part C. Okay, here we are given that B is a subset of A. So we have to prove these two things. So straight away, we take, let X be any element in B union C. Then X belongs to B or X belongs to C, which implies X belongs to A or X belongs to C. Why? That's because B is a subset of A. So if X is in B, then X must be in A. From this we get X belongs to A union C. Hence, B union C is a subset of A union C. Similarly, you can prove that B intersection C is a subset of A intersection C. In place of union, you just write intersection. In place of OR, you will have AND. That's it. So, similarly, we can prove that B intersection C is a subset of A intersection C. And I have said it before, again I am going to repeat. When I write something like this, it is supposed to mean that you have to complete it. Okay. So this is our exercise A. So now we move on to the, exercise 1. Now we move on to the second one. This one also has parts. Prove that these are especially easy. Commutativity of union and intersection, and A union B equals B union A. Intersection is associative. A intersection B intersection C equals A intersection B intersection C. These are so straightforward and easy and are available everywhere in any good book on set theory, or in any book where set theory is available. Most certainly these things are available. If they are already done for you. Most of all, we have already proved these things in the videos on knife set theory. If you go to those videos, you will find the solution here. So here I instead of solution I write like this. Do it yourself. Okay. The next one, of course, I will do, although it is also very easy. You see, we have already proved one distributive law, that intersection distributes itself over union. We are now going to prove the other one. Prove that A union B intersection C equals A union B intersection A union C. Here union distributes itself over intersection. That's how we say this statement. So here goes the solution. As usual, we will prove that each one is a subset of the other. So we start by showing that the left hand side is a subset of the right hand side. So let X be any element in A union B. Okay, to save us from writing this implies, which implies from this, we will just use the implication symbol. That will be more neat. So for that we should not start with let. We will start like that. We have X belongs to A union B intersection C. Implies X belongs to A. By the definition of union, this means X belongs to A or X belongs to B intersection C. Now this implies X belongs to A or X belongs to B by the definition of intersection, this. Now either X belongs to A, okay, or X belongs to B and C. Now this can also be written like this: X belongs to A or X belongs to B and X belongs to A or X belongs to C. You can simply think of this in usually like for example drawing a Venn diagram. This is just a rough way of trying to figure out the thing that is going on. A better way is to use the basic laws of mathematical logic. If you look at my video playlists, you will find a playlist that is entirely devoted to mathematical logic. There you will see that similar laws, distributive laws, are available for statements which look something like this. If P, Q and R are three statements, that is sentences which are either true or false, they are called statements, and this denotes OR. This symbol denotes OR and this symbol denotes AND. Then this statement is logically equivalent to this statement. we can use this to directly conclude that these two are equal. Just what we have to do is that we have to consider an element in any one of these sets and break that down like this and identify the final form of this statement with something like this, and that will get the job done. But without mathematical logic also you can think in general terms. I mean, in just ordinarily you can think in terms of Venn diagram. You see, x belongs to A or x belongs to B intersection C. Now what is B intersection C here? This is B intersection C, right? And this is A. Okay. Now x is either here or in both of them. So if x is here, then this statement is true, x belongs to A and x belongs to A. If x is not in A, then see, if this is not true, then since OR has to be true, the other thing has to be true, that is x must belong to B intersection C. If x is not in A, then x must be here, that means x must be in B as well as in C. So that means in this statement x belongs to B, so this statement is true, and this statement is true because x belongs to C. So that's why you are getting this. Using the laws of mathematical logic takes away this complexity of thinking of these things in this Venn diagram terms and the vagueness. It gets rid of this vagueness. So I would suggest you go through the videos on mathematical logic. There you will see, and there these proofs are also available. So there you will see that things are much more neatly presented. Anyway, so now we have to just make write these things more compactly. This means x belongs to A union B, and this means x belongs to A union C. Finally, this means x belongs to A union B intersection A union C. So any element in this set is here. So this set is a subset of this set. So this is a subset of this. Next, you take any element here in this set. We now have to prove that this is a subset of this one. So you see here the arguments will just be like this, only in the opposite order. I'm not going to explain much. You can figure out yourself what is going on. So y belongs to A union B. Because of intersection we have AND. Y belongs to A union C. This implies y belongs to A or y belongs to B. Or y belongs to C. This in turn implies y belongs to, in any case, okay, not in any case, either y belongs to, okay, if y belongs to A, then fine, we have y belongs to A, or if y does not belong to A, then since this has to be true and this has to be true, so y must belong to B at the same time y must belong to C. So that's why or y belongs to B and y belongs to C. So now any element in this set is here. So A union B intersection A union C is a subset of A union B intersection C. You can, if you want, you can give these relations some numbers so that you can refer to them back later. For example, right now we are going to refer to them. Thus from 1 and 2 we get what we wanted. And this completes the solution. Okay, then exercise 4. For a subset C of S, okay, S is some set and C is a subset of S. Let C prime denote the complement of C in S. Okay, I need ink. I should keep it more carefully. It's spilling all over the place. In S, okay, for any two subsets A and B of S, prove the De Morgan's rules. Okay. So what are the De Morgan's rules? They are very famous and very useful. They are named after the mathematician Augustus De Morgan, who introduced them. So the first one is this: complement of the intersection equals union of the complements, and the second one is just the opposite: complement of the union equals intersection of the complements. Okay, now the complement of a subset in a given set, it arises from that difference of sets. I think we have already discussed this, but anyway, you see, if these are two sets A and B, then we know what A minus B is. This is the set A minus B. It is the set of those elements in A which are not in B. Now, if it happens that B is a subset of A, then the set of those elements in A, this is also A minus B, that are not in B, but this is a special case because B is a subset of A. This set is said to be the complement of B in A, and this is denoted by this symbol B prime, or sometimes B superscript C, small c. C denotes complement. Here we are using prime. If you go to analysis, this notation can sometimes create confusion, because there when talking about sets in a metric space, sometimes this notation is reserved for the set of limit points of that set. We will see these things. Okay. For now, this means complement. So it is known that A and B are subsets of S. So both A union B and A intersection B are also subsets of S. So all the complements that you see here make sense. So let us now go through the solution. These things are rather easy, only we have to keep in mind the definitions and apply them properly. So to prove the first one, we start by showing that this is a subset of this. Let X be any element in A intersection B complement. Then X, if you want, you can include this, that X belongs to S and X does not belong to A intersection B, because it's in the complement of A intersection B. Now you see, this is the situation. This is S, this is A, this is B. This is A intersection B. So if X is not in A intersection B, then either X is not in A, or X is not in B, or X is in neither of them. Because if X is in both A and B, then it will belong to intersection. So that's why X can be here or here. Here X is in A but not in B. Here X is in B but not in A. Here X is in neither of them. So this implies X belongs to S and X does not belong to A, or X does not belong to B. Thus X belongs to S and X does not belong to A. Or we can write this whole situation like this: and X does not belong to B. Which implies this means X is in the complement of A prime, or, and this means that X is in the complement of B.